You're listening to Strange by Nature, your guide to the strange, weird, unbelievable, and improbable wonders of the natural world.
Hello, everyone, and thanks for being here today. I'm Kirk Mona, and joining me are Rachel Gimza and Victoria Thompson. We're all naturalists who together have scoured the world for weird and wonderful wonders, just to please your mammalian brain's desire for novelty. Isn't that nice? Let's do this.
Well, hello, everybody. Welcome to the show. We are all here again this week. It's so good to be with you.
Yay!
It is wonderful to be here once again.
I even am in my actual new recording studio space.
Lovely.
It's very
great.
exciting. Well, I start things off this week, and it's kind of a little bit of a Kirk topic, I want to say.
Ooh.
Yeah.
Interested?
Color me intrigued.
Okay. Well, all right. I'm going to start off by my section by saying Mars is a problem. Mars is a problem.
Mars is
All
a
right.
problem. I mean, I'll go with that. Sure. Why is Mars a problem?
I mean, of all the chocolate companies out there, I think we need to... Oh, you mean the planet?
The planet
Okay.
Mars.
Oh,
I gotcha.
that's different.
Yeah.
I got it. Got it.
Fair.
Well, the reason Mars is a problem is that it is way smaller than it should be.
What?
Ooh.
Yeah.
Okay. More interested?
Okay.
Tell me more.
Models of the early solar system show that the planet in the location where Mars is should have a mass about the same as Earth's mass. But instead, Mars has a mass of 0.107 of Earth's. So about a tenth of Earth's mass.
Yeah, that's not a lot, man.
Pretty small, yeah.
You know, Mars
very
is
wrong.
smaller, but also Earth
Yeah.
is actually especially dense for a planet. So,
Okay.
Yeah.
but it is at least 10 times too small. To understand
why?
this, we are going to have to back up a little bit and talk about the
I
sort
would
of
imagine, yeah.
common hypothesis of planet formation.
Okay.
So around young stars, there's a protoplanetary disk, which is a very large disk of gas and dust. And electrostatic and random collisions cause bits of matter to start sticking together, and they form tiny objects called planetesimals.
Okay.
This is all very simplified, of course.
Oh, so it has to be.
What?
I mean, first of all, I can't understand the actual science.
Oh,
Probably.
it's
stuff-
literal astrophysics.
Yeah.
Stuff attracts stuff.
Yeah.
There you go.
Gravity.
Once an object reaches about 1 kilometer across, it has enough of a gravitational field to start pulling stuff in that way as well. So rocky planets formed by this method closer in, where there's more dust. And then a bit further out, where things are colder, bits of ice also get accreted, which allows gas in the mix to kind of cool down enough to stick and create gas giants.
Interesting. Okay.
That's my understanding.
Yeah.
Great.
Probably wrong, but close enough. So meanwhile, there are also two opposing forces that are tugging at this material. There's the planetary wind, which is pushing gas out of the solar system, and gravity from the star pulling material back toward the center of the system.
I'm going to ask a question, and you
probably
probably
can't
won't
answer
have
it.
an answer, and it might come up later in the podcast. What is a planetary wind?
I was going to ask, is that
I think it's
different than the solar wind?
I think it's just like a solar wind.
Okay.
Okay.
I think
What
I
is
wrote
a
maybe down.
solar
I
wind?
wrote down the wrong thing. Probably. I think solar wind. It's
Because space is a vacuum.
It's particles escaping the sun.
yeah.
Got
So
it.
like the
We
ones
call
that
it a
cause
wind,
the
but it's not
aurora,
like air wind. It's particles floating
Yeah.
through like wind. Got it. Okay.
fairly fast moving particles
Yes.
ejected from the sun.
Got it. Okay. I'm there.
Okay, so the location of Mars is in an area of this protoplanetary disk that was thought to have been particularly rich in material. So Why is Mars so small? Big mystery.
Yeah.
Yeah.
There are also a few other mysteries and problems with the way the solar system actually is versus how the models say it should be. So
Yeah, there
one, if you assume that the rocky planetesimal, like that disk, that protoplanetary disk is much smaller than it usually is, you wind
Right.
up with so if it's instead of being this wide, it's, half as wide or whatever, you
Right.
wind up with Mars being about the size it is now. And this was found out in some simulations run by Brad Hansen and colleagues in 2009. But, why would it be smaller? Because based on the science and stuff, it should be a bigger size. Two.
So you're kind of saying all the rocks, the area of rocky material close into the sun potentially wasn't as wide as you would expect it to be.
So that Mars wound up the size it actually did. Because it didn't have as much material.
So in order for it to be the size it is, it should have been half the size that we're pretty sure the space of rocks was.
Something like that. I don't know if it's
Got
half,
it.
but yeah.
Yeah.
Smaller anyway. Okay, 2, the asteroid belt. You know that belt between Mars and Jupiter?
Yep.
It has both rocky debris, which would come from the inner rocky part of the system, and icy debris, which originates from farther out. How did these both wind up in the same place? This is a very vexing problem.
That's fair. I've never thought of that.
Yes.
Huh.
I mean, I didn't really know enough to think of it until researching this topic. 3, also, in other planetary systems that we have observed out in the galaxy, there are huge Jupiter-like gas giants that are up very close to their sun. We think this happens.
Pretty key piece of information there.
Yes.
Kirk
knows
so
where I'm
smug,
going with this, I'm
and
sure.
I'm just sitting here being like, space, man.
Space.
Yeah, it's cool.
It's so cool. Every time I learn something new about space, I'm like, man, universe is amazing.
It's so weird. So these gas giants that are up right close to their stars, we think this happens because these giant planets get caught in tidal interactions and get drawn in close.
Okay.
Obviously, that's not what we have here in our solar system.
It's the opposite.
Okay. So starting in 1999, some astronomers started to theorize that Jupiter could have indeed started to migrate toward the sun in the early solar system.
Yeah.
Ooh.
It's so cool.
Okay. But once they started to run this model, they realized that the presence of Saturn, which is also migrating inward, when they reached a certain position, these two planets would have been caught in a sort of a planetary dance where Jupiter orbited 3 times for every 2 orbits of Saturn, which created this 3-2 resonance. And through the magic of astrophysics, that
Beautiful.
would have then started them migrating back outward.
Right, because now they're attracted to the sun, but they're also attracted to each other because they're so big.
Yeah.
Yeah. Okay.
And there's gas, plumes that are in the way. There's all kinds of other stuff too. So Kevin Walsh and his colleagues were intrigued by the Mars problem and this possible migration of Jupiter, and they decided to run a computer simulation to address this.
Okay.
So this was, I believe, 2011. They placed Jupiter at a starting point of 3.5 astronomical units, which an astronomical unit is the distance from the sun to the Earth.
Okay.
Currently, Jupiter sits an average of 5.1 AU from the sun. Okay. So running this simulation, Jupiter slowly starts migrating toward the center of the solar system. This is in this combination of gravity and these currents of gas around the sun.
Right.
And as it did so, a sort of a snowplow effect that it created pushed and compressed the rocky part of the protoplanetary disk in toward the sun.
Okay.
It's shepherding all the material closer.
Yeah. Mars did not exist at this time, or at least wasn't in the spot where it is, but this left much less material in the region of Mars. So this accounts for why Mars does not have the mass it should have.
Huh.
Okay. Meanwhile, Saturn is a bit further out. It's also starting to get pulled in. As Saturn gets closer to Jupiter, the remaining gas between them gets expelled or drawn in and leaves the space between them clear, and this allows this 3-2 resonance to start up.
Okay.
And this resonance, for whatever reason, starts to force the planets to migrate back outward. Okay, Jupiter comes to a halt at 5.1 or 2 astronomical units, which is where it is now. Saturn comes to a halt at 7 AU, although later events would push it farther out from its current position, so now its current position is 9.5 AU.
Oh, wow. Okay.
It's really fun.
Yeah.
Yeah.
So, like, they do this, like, come in, go back out, just wandering planets,
We're just gonna
chaos throughout the
wobble a
solar
little bit
system.
Closer. Oh, I don't think so. We're gonna go further away. Oh my goodness.
This is called the grand tack theory. Tacking is what a sailboat does when it has to sail upwind, because it goes one direction and then the other. So it explains a lot. So it explains the mass of Mars, as we've discussed. It explains the current position Jupiter has, relatively far from the sun, unlike those close-in gas giants in other solar systems. But I had mentioned the asteroid belt before. Okay.
Yeah.
When astronomers first came up with this idea of Jupiter migrating in and then back out, they had thought that its doing so would have completely scattered and broken up the asteroid belt. So they thought, like, well, that can't have been what it'd have done.
How could that even be there? Yeah.
Right.
How could that be there?
It wouldn't exist.
In Walsh's simulation, with Jupiter moving very slowly inward, instead of scattering the belt, it sort of gradually pushes it further out, like almost sort of like, it's not magnetic, obviously, but I sort of think of it as like, you know, how two magnetic poles repel each other. It just kind of switches places with the asteroid belt. And then on its migration back outward, it kind of does the same thing in reverse.
Oh,
And
so it literally just swapped spots with the asteroid belt?
yeah, kind of. And, but also on its way out, it went much further than it had before, and it reaches the region where these icy objects were found, and then it starts kicking them back, deflecting them back inward toward the asteroid belt.
And then herding them up into a belt.
Yes.
Oh my goodness.
And it also makes our solar system more consistent with what we know about other solar systems.
Okay.
Because, like, just, I guess it was the particular arrangement of Jupiter and Saturn that caused the migration back outward. Otherwise, Jupiter would have been right up close to the sun. The way
Jupiter is amazing. Like, it's so big, and it has it's had a huge effect on our solar system and the shape of it and the planets. I mean, like, I've also heard it said that Jupiter, just being as big as it is, has had a big protective effect on the inner planets, because it just scoops up all the
a lot
crap
of the
heading
really
our
big
way.
Stuff,
asteroids.
Yeah, it's like a big snowplow that has it helped clear a lot of the debris out, and if we didn't have it, it'd be like we'd be less protected, which is pretty cool.
Thanks,
Jupiter.
Jupiter.
That's awesome.
Yeah, thanks Jupiter. You're great.
Yeah, that's what I have this week. I heard about this and I was like, Jupiter went for a stroll.
Love it.
Things you don't expect. Planets. I mean, okay, planets move, obviously, which is what I was about to say.
Literally what the word planets means.
Yeah. So, but planets going towards the sun and then moving away from the sun, don't expect that.
No, you don't.
My sources this week, there was a helpful article in Sky and Telescope magazine from October 2010. Another helpful article from NASA's Life in the Universe blog from August 2011. Also from NASA entry on How Do Planets Form. And then the article I mentioned by Kevin Walsh and his colleagues is A Low Mass for Mars from Jupiter's Early Gas-Driven Migration from Nature, 5th of June 2011. And then also some background information from Wikipedia.
Cool.
Amazing. Thank you.
Yes, that was very much a me topic.
Yes.
Yeah.
All right, we're going to take a short break and then we'll have an actual Kirk topic.
There we go. It's weird. I'm going to break your brain a little bit.
Oh, God.
Hey, everyone. Welcome back. At various times in my past, I've taken deep dives into genealogy.
Oh, yeah.
And I've gotten back into it a little bit recently, and I was taking some look at some parts of my family tree that I didn't explore as much in previous dives because there's so many different
ways you can go, facets.
Yeah, following different grandparents and things like that. But I think it's kind of fun to see like how far back into history you can get, and can you dig up the records and find what's out there. The problem is that records get pretty murky after a while. Lots of information usually dries up, at least in the part of the world that my family came from, like around the year 1500. It gets pretty tough to get past that year. People just didn't bother to record who married who and who had kids back then, especially if you were like a fisherman or a goat farmer or a dirt farmer or whatever, just nobody cared. No one wrote that stuff down.
I'm sorry.
People were illiterate,
I love the term, the very common term, dirt farmer. I do love it.
Oh, there was definitely some dirt farmers going back in my family.
People farming dirt. Just amazing.
I mean, a lot of immigrants who came to America came because there was just, it was tough. There wasn't much left to do there.
I'm not judging. I just think it's a kind of funny term.
I know. I love it. That being said, if someone asks me how far back I can trace my lineage, the answer gets weird because at least one line eventually, maybe, kinda, seems to trace back to nobility and then royalty, like Harold Bluetooth, whom Bluetooth technology is named after, is in my family tree. Okay. And once you get into the history of various Nordic royal families, they start to make all these dubious claims because, like, they're supposedly all related to these semi-historic kings or what sometimes appear to be wholly mythological kings.
Yeah, right.
You get people like Sigurd Snake in the Eye and Ragnar Lothbrok. Some listeners know who they are. And according to one particular lineage, I might be related to Halfdan Schilding, who was mentioned in Beowulf, which is pretty cool. He was said to be born sometime around the year 450.
Dude.
Wow.
Which is very cool. Never mind the fact that he was probably a mythical king that never actually existed. So,
right.
So probably not, right? But like when you get far back, some of these people started making stuff up to make themselves look better. So, but what I think is really cool is if you assume that this guy was real and that he really is like my distant relative, that means I could trace my family back through 44 generations, which would
That's insane.
Crazy. And of course, just a reminder, this guy was mythical, so probably not, right? But even if we take some of the more conservative lineages that actually have like good documentation for, I can easily get back to the 1400s, which is something like 20 generations back.
Yeah, wow.
And so why all this talk about genealogy? There's actually a joke in Norway that like everyone is related to the old kings because everyone can trace their lineage back to them eventually.
Right.
But it turns out it may not be really a joke. I recently came across an interesting article and it utterly broke my brain. So one thing you realize when you start to look at a family tree is that the branching pattern it gets out of control pretty quickly. I have two parents, but they each have two parents. So I have 4 grandparents who each have 2 parents. So 8 great-grandparents, 16 great-great-grandparents, 32 great-great-great-grandparents, and so on. And this doubling
even count like their siblings and stuff.
No, right? Right. That's just those that's not counting third cousins and all that crazy stuff. This is just like the direct line. And so it gets out of control pretty quickly. If we go back just 33 generations, which doesn't seem like that many.
33.
But like that's not 33 is not a huge number.
Right.
No, it's not. Generation-wise, it's giant.
If we go back 33 generations, at least mathematically, if you look at all those sort of grandparent slots that you'd have to fill,
is
8 billion. slots where you need to put people in
Well, that doesn't
if you're
seem
filling
right.
out your tree.
I
Spotted, right?
Yeah.
This is problematic.
Yeah.
And keep in mind, that's just at the 33rd generation. The 34th that's going to double.
Yeah.
Right? So
no.
it goes up and up and up.
Math is fun.
That's an impressive number, but it's also a really problematic number because that is more people than there are currently on the face of the earth, and certainly more people than there were back then. And using my family as an example, 33 generations back gets us right around the year 880. And interestingly, scientists that generally say that assume that like a generation is about 30 years. If you multiply 30 by 33, we get 990. It's pretty close to where it plays out in my family tree. And so if we subtract, if we subtract 990, that was wrong. Doesn't get to the year 990. That's 990 years. So if we track that from 2026, we get 1,036. So obviously your family tree may vary, but generally we feel like 33 generations is 1,000 years. Okay. So if you go back 1,000 years, you have 8 billion great, et cetera, grandparents. Lots.
Except you don't.
Except you don't, right?
You don't.
Because there are lots of estimates for the size of the human population back around the year 1000.
And it was not 8 billion.
No, they're all in the ballpark of like 400 million people worldwide. And clearly, like, people from the other side of the world were not part of your family tree, right? So you kind of look at that and go, this doesn't make any sense. There's more theoretical grandparents than there were people on Earth by a lot. And the solution is actually pretty simple, though. Especially in countries with small populations that were interbreeding, the same people are likely filling a lot of those slots.
Yeah.
Because you're related to the same people through many different, and not interbreeding in like a, the
not
way you might think of it today.
Necessarily.
Marrying your brother or sister or cousin, something like that.
Well,
it basically
probably
the idea
there's
is
some of that cousins probably.
No, there definitely was some of that back then. But I mean, like, it's the kind of thing where even someone from the next village over, just you go back a few generations and they're probably your third cousin or fourth cousin. And so when you compare your family trees, the same person is going to appear from two different lineages that are going to converge. And so a lot of those 8 million slots are just the same names over and over and over and over again.
And for whatever percentage of the world, one of those people is Genghis Khan, right?
Right, yeah.
Absolutely.
So just as the tree grows, I think one way to think about it is just as the tree grows, like widens out as you go back in time, it also widens out as you go forward in time. One person can give birth to millions of descendants and many generations down the line. Some of them are gonna marry each other without even knowing they shared this single common ancestor. So those names will appear many times. A coworker and I actually figured out not too long ago that we actually share a common ancestor. Pretty far back, like in the 1800s. We're like, oh my gosh, like we have the same, like, this. It was like a distant cousin to each of us. It wasn't like a direct descendant, but it's like, oh, cool. We found the spot where our lineages overlapped at least a little bit, which is fun.
Absolutely wild.
But this brings up an interesting question. How far back in time would you need to go to reach a point where everyone on Earth has a common ancestor? Right?
Well, there have been some genetic bottlenecks, haven't there?
Yeah.
There have been, And that's kind of where my brain would go too. Like, oh, this is a genetic bottleneck. There was a time when we think humans maybe were down to just 30,000 people, I think, on Earth. And they're like, well, that would be a good candidate. Because, if you can go far enough back in time, I'm related to all my coworkers, right?
Yeah.
I'm related to both of you if you go far enough back in time. I'm related to everyone listening. I'm related to my dog if you go back far enough in time,
That's
right?
true. That's true. That is how the tree of life works, yes.
Yeah, we've talked in the show about Luca. I think, Rachel, you talked about Luca, which is the last universal common ancestor. That's like of the creature that all animals on Earth could trace their lineage back to.
Right.
There's actually a similar concept for humans called MRCA, which is the most recent common ancestor. So we're going to make a little game of this.
Oh, man.
If you consider all of the people on Earth, of all the races and countries of origin, however you want to look at it, how many years back do you think you would need to go to reach this person who was the most recent common ancestor to all humans on Earth?
I'm going to say 100,000
Like how many generations back?
No, how many years?
100,000 years ago. That's what I'm going to say.
So Victoria says 100,000 years. I realize we're just pulling these numbers out of thin air.
Yeah, we are. I'm gonna go.
What's your gut check?
Not totally thin air.
Sure.
Yeah.
Because I know like the approximate age of some of the great migrations to different parts of the world. So it has to be before that.
Right.
Yeah.
Okay, yeah.
So I'll go Price is Right rule.
There's no prize for going over by one.
Yeah. 94,568 years ago.
I think my brain was kind of in a similar space to all of you, like a long ass time ago.
Yeah.
Well, buckle up. This one broke my brain. It appears the answer is about 3,000 years.
What?
Doesn't make any sense, right? No. So when I heard this, it absolutely short-circuited my brain.
Because we have
I know
evidence of what?
There's some people in like Australia.
I know. It's because we're thinking about the question wrong, is what's going on. Like when I heard this, I instantly knew, I'm like, this article's wrong. Like if we go back way further than 3,000 years, humans were living incredibly separate lives on opposite sides of the earth. The idea that we're all descended from a common grandparent that was alive 3,000 years ago sounds like some kind of like young earth conspiracy theory nonsense, right? However, this isn't some wild conspiracy theory. It's based on science and mathematics. So let me tell you what's going on here. One of the people to really dig into this was a mathematician named Chang, who published a paper in 1999 where he actually argued that the most recent common ancestor of everyone currently alive on Earth was just 1,000 years ago. And people rightly were like, come on.
So
there's no way that's right.
Are you on?
And so what Chang had actually done was look purely at the math. With every generation you go back, you're related to more and more people. As we saw at the start, 1,000 years ago, you have 8 billion ancestor slots, which is way more than there were people on Earth. So what he showed mathematically is that once you reach that 8 billion mark, statistically, there will be one person who shows up in everybody's family tree. Well, that's all well and good, but we live in the real world, not in a math problem, right?
Right.
There are very real geographic barriers such as oceans that have kept, say, Pacific Islanders very far away from Norwegian goat herders. Like, they were not interbreeding. We're not sharing ancestors and whatnot, at least not, And so what actually happened is Chang and other researchers revisited this math problem a few years later in 2004. And this time, their computer models accounted for mass migrations, isolation, like all of the real world human factors that actually affect how people move around the world. And this time they came up with the answer of 3,000 years. And it still seems like a bonkers number.
Yeah.
But here's the thing. We're thinking about it wrong. I think we're thinking of like, oh, there was this one person who then like gave birth to the world population.
Year. Right.
And that it's not that we all trace our lineage back to this one starting point. This is the first person we can trace back to that we are all related to that shows up somewhere in our family tree. And the idea is that, it really just takes one person from another part of the world marrying into a family to potentially eventually spread DNA to everybody on a continent after many generations. So you may say, oh, this continent was cut off from others for thousands of years. It's like, yeah, but not now. We live in a global world where we are super interconnected. And when you do DNA studies, you find people around the world at some point have had contact with people from other parts of the world who have had contact with people from other parts of the world who've had contact with people. It really only takes one little thread for one of those 8 billion people to end up being related to you. So I did some looking at this. At this point, there really is nobody on Earth who's just from one place. our DNA has gotten, mixed together really well. 3,000 years ago is not 33 generations like we were talking about earlier. It is 300 generations.
Oh,
so
okay.
33 generations was 8 billion ancestors. I actually looked at the math on this. 300 generations is 2.04 novemvintillion ancestors.
Yeah, what's that?
What number?
If you aren't familiar with
notation, please,
number,
Kirk.
novemvigintillion, which I had never heard of.
Is that 29?
How many zeros?
That is a number larger than all of the atoms in the known universe.
Okay, then. So
that's how many ancestor slots you have when you go back just 3,000 years. So you can start to see why eventually you get to a point where it's like everybody appears in everyone else's family tree.
Right.
Also considering if you go back 3,000 years, there were only 50 million people on Earth. So the overlap of common ancestors is enormous. Statistically speaking, there's at least one person who would be found in the family tree of every human on Earth that is alive today if you go back 3,000 years.
Yeah, I guess you start to think about it. I just started reading this book about the Silk Roads. And, like, people got around. People traveled from China to Europe.
It takes one person.
Alexander and his army traveled from Europe to India, and all the Mongol hordes and all the various,
people get around. And when they get around, they get around. So, that just kind of blew my mind. We don't know who this person was. Like, there's no way to tell. They could have been a king, right? They could have been a nobody. Like, odds are they were just some average person living their life, which is kind of a cool thought. Like,
I like
that. If you have kids today, and here's the key, your lineage keeps on going.
Yep.
And a lot of them don't. Most of them don't.
Right.
But if just one of those little threads keeps going for thousands of years, you too could someday be the most recent common ancestor for humans. Someone alive today is going to be the most recent common ancestor for humans 3,000 years from now. Somebody is going to, their line is going to keep on going that long. Obviously, because, assuming we're still here in 3,000 years, that means someone's line continued on. This broke my brain. It was so much fun to read
so
about.
So unintuitive. It's amazing.
Yeah, let it really sink in. If you want to know more about it, my sources were the research paper by Chang, Rode, and Olson, which was in Nature in 2004. But there's also a nice sort of recent summary in the online magazine Space Daily. And it's just a really cool brain-breaking topic about how we are really all related, and even more closely than we might imagine.
Huh.
Food for thought.
So to all my brothers and sisters, you enjoy this break, and we'll see you soon.
Oh, no. My brain hurts, Kirk. Thanks for that.
I know.
Wasn't enough of a break.
Wasn't
it's still
enough.
Wild. Wasn't enough. Well, we can pop some more ads in or something if you want.
No, it's fine.
Okay. I don't think anybody wants that.
No, we won't do that.
Except for our lovely patrons who didn't hear any ads, because that's what you get. You get ad-free episodes when you're a patron.
That's true. So on this show, I have what I think is a fun topic for y'all. On this show, we've talked about comb jellies before, several times, in fact. And they continue to be truly phenomenal creatures, okay?
Mm-hmm.
However, when all the times that we've talked about comb jellies, we have yet to talk about the largest comb jelly there is.
Ooh.
So let's talk about the Cestum veneris, also known as the Venus girdle.
Venus girdle.
That is what it is called.
Okay. All right.
Love it.
It is literally the largest species in the entire phylum.
Oh,
okay?
Wait, what?
So
this is the largest species
No, I
in
heard
the
you.
phylum.
I heard you.
Mm-hmm. For those of you who can't remember the taxonomic breakdowns, because I know that I forget all of the time, when you are organizing a species or organizing animals or anything, it goes kingdom, then phylum, class, order, family, genus, species.
Mm-hmm.
Do you have a particular little verbal trick you use to remember those? There's a whole bunch of them.
Kirk, I just mentioned that I forget about it all the time. I do know that there is a fun verbal trick. I never remember the mnemonic that helps you remember.
Something about King Philip's sandwiches or something.
Oh, right. I just somehow memorized just the words in order when I was pretty young, and it's stuck forever.
I heard King Philip's before. I don't know. That's all I got. So it's somewhere. Like, I didn't write it down.
King Philip's something.
Yep.
There's a bunch of really good ones. Maybe we'll share a few in the bonus on this episode.
So the fact that this is the largest in the phylum is a pretty big deal.
It is.
Literally a big deal. It's the largest in the phylum. Haha. Okay, so in your head, I hope everyone groaned at that, by the way. I'm like thinking everyone did. In my head, you all did groan. So in your head, I want you to picture a jellyfish.
Mm-hmm.
Okay? Venus girdle does not look like that. Okay? So Venus girdles are more like transparent ribbons. All right? So picture a large transparent ribbon.
Okay.
And along the edges of that ribbon, which is pretty common for a lot of ribbons, it has like these tubular canals running along the edge. Okay.
Uh-huh.
A lot of ribbons have like a border. Think of like the border of a ribbon.
Sometimes there's wire in it.
Sometimes there's wire. So these tubular canals that are running has bioluminescence.
Ooh.
Which activates
Love it.
when it's disturbed. And it's not just one color, it's quite literally a rainbow.
Oh my gosh.
And it will do all of the colors of the rainbow along the edge. It is absolutely beautiful. Generally, this comb jelly is curled up. In one of my sources, it actually equated it as looking like a cinnamon roll. Like it's curled up like a cinnamon roll.
Okay. All right.
Which is kind of fun. It does spend some time like that.
Does it taste like cinnamon?
I don't think anyone's tried eating it, Kirk, but you're welcome to try.
Well, missed opportunity.
Right. Well, there's a reason. So
I bet there is.
Yeah. So part of it is because they're found all over. They're in the open ocean worldwide. In the tropical and subtropical regions.
Cool.
They're not hanging out near the surface. They're hanging around mid-water, which is part of the reason why they have that bioluminescence, but they're not like deep ocean critters. So we're not like going to touch them while we're swimming.
Yes, no thank you.
Also, we're not going to be in the pelagic swimming generally. So that also is something.
Generally, no.
Generally, nah. So because they're in that open ocean, they're able to stretch out and use their bodies that have like somewhat sticky substance on them to collect and eat small crustaceans. They are predators. They are actively swimming. As we've noted with comb jellyfish before, they have setons, which help move the girdle through the water. There's 8 sections of them, and they act kind of like paddles to help them move through the water to get to where they need to go. Their mouth is in the middle of their body.
Oh.
So that ribbon, right in the middle of that ribbon is where their mouth is. Depending on the source, this creature can measure 120 centimeters or almost 4 feet. So from one end to the other.
Now, Rachel, is it always rolled up like a cinnamon roll, or does it sometimes unroll? Okay.
It will unroll, yes.
Okay.
So it's not always in the cinnamon roll shape. It's often in that, but it's not always. It will extend itself out. Now, depending on the source, that's either their length or their width. I tried to figure out which one it was, but all my sources, everywhere I looked, had either length or width. There was no, like, I think it depends on how you look at it, which end is which end, you know?
The long dimension.
Yeah, exactly. So 120 centimeters is pretty long and almost 4 feet. That's not quite a Rachel. But the width or the length, I guess, the other measurement, the short measurement, is 2 inches or 5 centimeters.
Okay.
So truly like a ribbon. And they're long and flat. I keep describing it as a ribbon. They are flat. They're just really beautiful little creatures. They don't sting. They don't have that typical comb jelly venom. They
so
just
maybe
kind
we
of
could eat them as cinnamon rolls.
Could potentially.
Let's not.
They probably don't taste good.
No.
They just are swimming through life, eating all sorts of crustaceans, whatever they can catch, looking beautiful with their bioluminescence. They're the biggest in their phylum, which is pretty insane to just think about. It's a short and sweet topic today. I just wanted to talk about this beautiful little jelly. I'm sorry, this big,
very cool,
gorgeous jelly.
Big, yeah. And I assume we can see them on our social medias and most importantly in our email newsletter.
Yes. Oh my gosh, it's beautiful. Like there was Woods Hole, one of the places that I was looking, had a nice video of it that they had captured. And it's gorgeous.
Does it change color rapidly?
Mm-hmm. Yeah. So it looks like an undulating like rainbow going through, and it's some sort of signaling too. It's just it's.
I'm gonna have to check that out.
Oh yeah. So my sources this week were Woods Hole Institute, Wikipedia, Nerdist had a solid article, and a spot called Why Knowledge Discovery, which was also really good. That is what we have for you this week. Couple brain-breaking topics this week, and then a beautiful rainbow comb jelly.
Wow, what a show. Awesome.
Wild. So thanks everyone for listening.
Yeah, thanks.
Yep.
Yeah,
see y'all
have a good
next
night.
week. Bye.
Bye.
Thanks everyone for listening to today's show. Be sure to subscribe. New episodes drop every Wednesday, and we love sharing this strange world with all our listeners. If you would be so kind as to leave us a 5-star rating and review wherever you get your podcasts, that would be great. It lets other lovers of the strange discover the show. You can reach us by searching for Strange by Nature Podcast on Instagram, Facebook, and Blue Sky. You can send us an email as well. Our address is contact@strangebynaturepodcast.com. If you want more information about the show, you can check out our website, strangebynaturepodcast.com, and you can support the show and get ad-free episodes at patreon.com/strangebynature. Until next week, get outside, stay curious, and embrace the strange.